You're an astronaut orbiting 400 kilometers above Earth when suddenly an alert flashes across your display. The system responsible for producing the breathable air on board has failed. Now, you and your crewmates must work with mission control to identify the problem and fix it as quickly as possible. This might seem like a scene from a sci-fi thriller, but for astronauts on the International Space Station, dealing with situations like this is a reality of life. For over 25 years, ISS's air supply systems have revolutionized space missions. Yet the need for regular maintenance, repairs, and upgrades has pushed engineers to develop even more reliable systems for future spacecraft. Creating breathable air in space has two requirements: supplying oxygen and removing exhaled carbon dioxide before it builds up. Every astronaut in space needs, on average, about 0.8 kilograms of oxygen a day. Most early space missions met this demand by storing oxygen on board in pressurized tanks. For example, the 8-day Apollo 11 mission to the moon carried 3 astronauts, along with around 50 kilograms of oxygen for life support, more than enough for the crew to survive on. Canisters containing lithium hydroxide would chemically react with carbon dioxide, scrubbing it from the cabin. But the launch of the first space station marked a turning point. For the first time, crews would remain in orbit for months, not days. A typical 6 to 8 month expedition with 7 crew members might require over 1,000 kilograms of oxygen, demanding about 30 large tanks. And constantly shipping this massive load to and from orbit would be expensive. So engineers developed a solution using water and a process called electrolysis, a system that makes oxygen directly on board. Water is relatively easy to come by on the ISS, thanks to its robust recovery system. It captures nearly all moisture on board, from sweat, exhalation, wash water, and even urine, and purifies it into fresh, potable water. This clean water is routed to an electrolyzer, a device equipped with 2 electrodes, one positive and one negative. When an electric current is applied, the electrolyzer breaks down water molecules into oxygen and hydrogen gases. Oxygen collects near the positive electrode, and hydrogen gas bubbles form near the negative electrode. But there's a problem: getting these gases out of the water. On Earth, bubbles naturally float to the top of denser liquids due to gravity. But in orbit, where everything is in free fall, bubbles tend to cling to the electrodes. One solution is to pump water through the electrolyzer, carrying the bubbles away to a separator. Here, the gas-filled water is spun, much like a washing machine in its final spin cycle, forcing the liquid outward while the gas collects in the center. In the end, oxygen is released into the cabin. Hydrogen gas is either vented into space or routed to a reactor, where it combines with captured exhaled carbon dioxide to make methane and water. But this system isn't perfect. The process for separating bubbles from water relies on many complex moving parts that are prone to breaking or malfunctioning. And as space agencies set their sights on expeditions deeper into space, like year-long crewed trips to Mars, this approach becomes increasingly impractical. So researchers are exploring new ways to separate out this gas. One promising solution is to spin the gas-filled water inside the electrolyzer using magnets. This system takes advantage of a fundamental property of how electrons and magnets interact. When negatively charged molecules move perpendicularly through a magnetic field, the field applies a force on the molecules called a Lorentz force. It pushes them sideways at a right angle to both the electric and magnetic fields. So, by positioning the magnets and current path In just the right way, this Lorentz force can swirl the liquid, separating out the oxygen and hydrogen gases. No pump or separator needed. This magneto-hydrodynamic oxygen generation assembly, or MOGA, has no moving parts, so it requires less maintenance and replacement hardware, freeing up space on board and allowing astronauts to spend more time on other endeavors. MOGA is still in the research phase, but it holds promise. With a more robust oxygen system, astronauts on future space stations and deep space missions should be able to breathe a little easier. Not ready to come back down to Earth? Watch these videos or subscribe to our channel to keep exploring the science, philosophy, and mystery of the universe.